Good evening everybody. So today we'll see about the other part of the charge transfer transitions if it originates from the metal center. So what we have seen so far that during all these transitions several orbitals are involved which can either be based on the metal or based on the ligand. So these orbitals which are based on the metal and ligand, they are very important to play in these charge transfer transitions because they are highly facile transitions because there is no such restrictions for the corresponding electronic charge transfer. So if this particular one, that means the metal orbitals, if they can function as a donor orbital and the ligand can function as an acceptor orbital, then what we expect? We expect that there should be corresponding charge transfer from the low lying metal orbital, which is the donor orbital, to the acceptor orbitals which are higher in energy, and as a result we get the corresponding metal to ligand charge transfer transitions. And there are several examples of such transitions which are very much useful in determining not only the corresponding concentrations, the unknown concentrations of the metal ions, but sometimes the corresponding characterization of the metal complexes. So these things we should have in our mind, and where we will find that since the metal is behaving as a donor orbital, when we move from the corresponding ligand field theory to typical molecular orbital theory, we will find that we are not talking everything in terms of the corresponding crystal field splitting, where we do not accept that metal orbitals are overlapping with the ligand orbitals. But in typical molecular orbital picture, what we see there, that some of these metal orbitals do overlap with the ligand orbitals, and we can have certain orbitals which are mainly of metal character, that means of certain percentage character which is of metal character, percentage of metal character, and in some other cases where we talk about the corresponding mainly ligand orbitals, say they have certain percentage of ligand character. So these are the things basically important to know, the amount of charge transfer which is taking from these particular centers from one point to the other. So what we see that when the metal center is responsible for donation of electron, that means metal should be highly reducing in nature, that means it has some excess electronic charge, that means they are in low oxidation state. So these species will be in low oxidation state, and these low oxidation states are there. We have certain metal ions, and those metal ions can be in the zero oxidation state also, or M1 plus or M2 plus oxidation states, and in all these cases most of these corresponding orbitals which are available for the free ion are all filled. That means some of these orbitals which are available to them are filled. That means filled orbitals are available for donation. So, these field orbitals will basically be there which can donate the electron density to the ligand orbitals. So, we will see how these particular transitions can help us in understanding the corresponding metal complexes. So, we have the MLCT type of transitions, and already we have discussed the other one, the complementary one, where the ligand orbitals are the donor orbitals, and there we have seen that the particular ligand to metal charge transfer transitions which we see typically for certain systems. And we have seen that some of these pi and sigma electron densities are responsible, and the donation is taking place from some of the orbitals which are having metal character to orbitals of ligand character. So, next what we will see that there are certain of these metal centers present which commonly accept electrons rather than donate them. So, examples of such pi accepting ligands are therefore that which can stabilize the corresponding metal complexes in low oxidation state. That means what we see, if we have the carbon monoxide as the ligand, what happens to that is, if we have the nickel which can form very nicely the corresponding tetracarbonyl nickel 0 compound, or iron which can also form the corresponding pentacarbonyl iron 0 compound. So, they are having all the levels which were available for the corresponding metal center is in 0 oxidation state. So, they have large number of such field orbitals available for donation to certain orbitals which are of ligand character. So, if these orbitals are available, and we see that in case of nickel we have the corresponding electron density is T2G6 and Eg2. So, the required number of electrons what we can have, we have two unpaired electron densities in dz square and dx square minus y square orbitals. And these orbitals are basically of sigma character because they are directly facing the corresponding ligands which are in a tetrahedral geometry. But if we consider them as the corresponding orbitals which are present for TD geometry, the situation is completely different from that of our distribution for the octahedral geometry, because this particular arrangement is for OH symmetry, but for TD symmetry we have the three orbitals over here, and we have the E set and the T2 set. So, we have 1, 2, 3, 4, 5, 6, 7 and 8 electrons for the nickel in plus 2 oxidation state, and apart from that, when we just consider it is a 0 oxidation state, we have 2 more electrons if it is in octahedral geometry, and if it is in tetrahedral geometry we have a situation like this. So, if we consider that all the 10 electrons which are coming for donation to the ligand orbitals are all filled. So, this T2G set is the dxy, dxz and dyz set, and they are in between the corresponding Cartesian axis which are present for the octahedral geometry, but which can be close to the corresponding tetrahedral orientation of the corresponding ligand system. So, if they can donate the electron density from there to some of these orbitals where we have the carbon monoxide molecular orbital. So, if we see the corresponding molecular orbital picture of the carbon monoxide, it tells us that it can have the corresponding pi electron density which is originating from the corresponding pi bond between the carbon and oxygen, as well as it has the corresponding anti-bonding orbital which is pi star. So, if pi star orbital is available for its corresponding acceptance, that means if they are behaving as the corresponding acceptor orbital, then certain amount of charge from these orbitals, which are mainly metal centered, can be pushed to the corresponding ligand acceptor orbital. That is why, since it is accepting the corresponding electron density, it is behaving as a corresponding pi acid. So, these orbitals which are there, which can be functioning as corresponding pi accepting ligands. So, typical example is carbon monoxide, same is true for nitric oxide, Cn minus, cyanide, nitrogen, bipyridine and orthophenanthrene. So, likewise, if we have the corresponding nitrogen centered bidentate ligands like bipyridine and orthophenanthrene, we will find it has also some pi electron cloud, and those pi electron clouds are there for the corresponding bonding pattern, and for antibonding state we have also the corresponding pi star level. So, isocyanate, then cyclopentadienyl and the double bonded carbon system or triple bonded carbon systems all are having multiple bonds between the atoms, whether it is carbon-carbon or carbon-nitrogen system. So, whenever we have a sigma bond as well as pi bond, it can definitely have the corresponding pi star antibonding level. So, all these pi star antibonding levels, when they are utilized for acceptance of electron density from the metal center, we have the possibility of getting the corresponding charge transfer transition, which can be considered as their characteristic metal to ligand charge transfer transitions. So, if the metal, already we have seen that the metal can be in the low oxidation state and the ligand possesses low lying empty orbital. What is called this low lying? Because the energy of this orbital should be accessible for the transition. If it is in a very high energy region, we definitely not get the corresponding transition in the visible region at least. So, the system will not be colored. So, to get a corresponding colored system, we should have the corresponding transition in the visible region. So, the corresponding level, which is pi star level, and this is basically metal sigma orbitals or the corresponding metal based pi orbitals are there. And if this energy gap, which is important, which is delta E, it spans for the corresponding range basically in the visible region, then only we expect certain transition, and which can be characterized as the corresponding metal to ligand charge transfer transition, and which can be seen as the corresponding colored solution for the visible region transition. So, we have the corresponding level which can consider as low lying empty orbital, which is acceptor in nature. So, for carbon monoxide as well as for cyanide ion, we have the corresponding transitions, such as when it is bound to nickel center or it is bound to the iron center. Similarly, for ferrocyanide and ferricyanide system, iron is bound to the cyanide ions, and then an MLCT transition can occur. So, all these MLCT transitions may take place when we have the situation belonging to these ligands like this or the other set of ligands what we have seen just now. So, this is one pictorial representation, a very simple pictorial representation what we have seen just now for the level. That means, what are the corresponding levels for this M sigma or M pi type. What we can see that if we have this particular sigma type of orbital for octahedral case, we have the T2G type of orbitals or the EG type of orbitals which are available for the corresponding octahedral complex. So, if we have a D5 uncoordinated metal centers like Fe3 plus, which is a 3D5 system. So iron, if it is there, and particularly when it is forming such complexes with the ligand, it is forming the corresponding low spin compound. So low spin iron compound is forming over there, and in octahedral geometry it will have the corresponding electronic configuration of T2G5, and that T2G5 electrons will be there, and we have the corresponding other metal orbitals which are empty. The Eg level is also available over there, and we have the ligand pi star orbitals which are of ligand character. So these orbitals are of metal character, mostly they are having some certain percentage of metal character, and if we find there is a mixing of the metal and the ligand character, here the corresponding metal character we can find it out from some calculations nowadays, for some certain amount of certain sophisticated calculations like density functional theory based calculations, where we find the percentage of the character of these orbitals, and when we push the electron density from this level to the upper level, and where we have the corresponding ligand pi star level, and the transition is mostly probable for the corresponding range where the T2G level of electron density is giving the corresponding charge density to the ligand pi star orbitals, which are highly allowed transition, because it can have certain transitions to the Eg level also, which will be for the corresponding DD transitions which are not allowed transitions, but due to some vibronic coupling or some other relaxation of the rules, the Laporte selection rule, we can have certain amount of transition which can be considered as the DD transitions. So apart from these DD transitions, we can have highly intense charge transitions, charge transfer transitions to the corresponding ligand acceptor levels. And if it happens, we have the corresponding lambda max values also. If it is colored, it can be in the visible region. We see the color in the visible region, as also the corresponding epsilon max values which are of say several thousands, say 50,000 or so in mole inverse in centimeter inverse unit. So this particular charge basically giving us certain amount of these values. So for D5 complex, we can have the corresponding metal to ligand charge transfer in an octahedral complex. So in an octahedral complex, the corresponding energy diagram for the transition would be like this. When we have the corresponding absorption of irradiation, so when the complex is irradiated with light of certain wavelength which can be absorbed, then the electrons in the metal orbitals or the metal based orbital, which are certain percentage, say 80% or 70% of metal character, are excited to the ligand pi star orbital. So this is the main mechanism. So we can ask ourselves that what is the corresponding mechanism for typical MLCT transitions. So what we have seen in other case where we have a different type of mechanism for LMCT transitions, now we have completely opposite type of transition for the metal to ligand charge transfer. So these sort of charge transfer play some important conclusions to us, like that what we have seen, the ligand to metal charge transfers. This is, we have seen, we already discussed this thing for KMNO4. When we dissolve it in water, it gives intense charge transfer band, and to absorption below what we see now, that what type of transition we can have when we record within a corresponding spectrophotometer, it results basically the corresponding transition like this. So when one particular band which is structured is around 528 nanometer, so if we measure this particular one in corresponding spectrum is giving the corresponding band at 528 nanometer, which is due to the corresponding pink coloration of this, and some other transitions are also there which are of corresponding less intense, which is in the lower region of the wavelength, which is around or less than 320 nanometer or so. So, this intense charge transfer band, which is a corresponding dilution at the 10 to the power minus 5 molar, we have an absorbance value of say 2.5 or so. So, we can get this in the corresponding spectrum. So, this 528 nanometer band gives rise to the deep purple color. It is the color due to the solution and electron from an oxygen lone pair. So, oxygen, all the 4 oxygen atoms in KMnO4 what we have seen, that we can consider them as the corresponding field level. So, whenever we have in a tetrahedral geometry of this MnO4, and in the terms of the corresponding hybridization scheme, what we know like that of our methane molecule, we have sp3 hybridization scheme. Similarly, for this one we can have the corresponding sd3 type of, that means the d orbitals are involved for the corresponding tetrahedral geometry. So, involvement of these d orbitals for the corresponding tetrahedral geometry tells us that this has 0 electron density for the 7 plus oxidation state, and all the oxygen atoms are 2 minus, 2 minus, 2 minus. So, they are all filled. So, we have the generated vacant orbitals. So, all the metal ion orbitals are vacant now. It can accept the electron density from the filled ligand orbitals, which are filled on the oxygen. So, oxygen orbitals basically the corresponding s and p orbitals. So, rather the p orbitals basically are available for donation to the metal centers. So, the transition is basically if it is completely p centers to d of the metal ion. So, it is highly favored transition. So, we have a huge intensity for this transition from the oxygen to the manganese center. So, now we have in this particular case what we have discussed also earlier, that in this particular case we have low lying manganese orbital. But in case of what we are discussing today, for the metal to ligand charge transfer transition, we should have certain other type of orientation where the metal orbital giving us the corresponding low lying orbital. So, one such example is the tris bipyridyl ruthenium compound, ruthenium complex. So, ruthenium is in +2 state. It can also be seen for iron compound, but this intensity is very good and the corresponding band for this charge transfer is very much characteristic for this compound. So, whenever we make this compound, because it has some good catalytic properties to show for this tris bipyridyl ruthenium 2 chloride compound. So, when we dissolve in water and this particular compound basically gives a charge transfer band, it can be dissolved in acetonitrile, it can be dissolved in dichloromethane also, where it gives the corresponding charge transfer transitions. So, charge transfer transitions will now take place from metal to these ligands. So, we have 3 bipyridyl ligands. So, this is one bipyridyl, this is another bipyridyl, and this is another bipyridyl ligand we have. So, now we have again certain type of the structured transitions like what we have seen just now for KMnO4. So, we have certain these transitions. So, these are 200, 300, 400 type of this is not 30, 40. So, this particular transitions what we see that structured transitions which is mostly centered over here, where this particular one around 330 or so, the d electron from the ruthenium atom is excited to the bipyridyl antibonding orbital. So, we have this bipyridyl ligand So, this is the bidentate NN donor ligand what we have in our hand, and this is attached to one ruthenium. So, 3 such ruthenium species is there, and these are all neutral. So, from the point of view of any other charge separation during complexation is not taking place, and overall charge of the complex would be 2 plus. So, that is why we have 2 counter anions as the chloride anions. So, we have C double bond N here, particularly if we just focus our attention on this. Similarly, we have another C double bond N. So, we have large number of, that means the 6 such C double bond N bonds are there, which is present, also present in such imine bonds. When we get these imine bonds from the ship bases, so they also give rise to those imine bonds. So, we have the corresponding bonds when they are forming between this carbon and nitrogen. Basically, we have the sigma and the corresponding pi bond. So, whenever we forming this particular bonds, so what we have seen that the typical organic compound, that means when we talk in terms of the corresponding isolated bipyridine molecule, what we see that we have the sigma bonding level, then the pi bonding level, and if we have certain amount of lone pair of electron, because these nitrogen lone pairs are available over there. So, these nitrogen lone pairs are basically utilized for the donation to the metal centers. So, we have the n electrons, the non-bonding electrons, and these n electrons are basically engaged in forming the corresponding bonds. So, if we find that there are 2 such n electron, the non-bonding electron, and if they are basically donated, so if we have these non-bonding electrons on the nitrogen, they are basically donated to the metal center for the corresponding coordinate bond formation. So, we have on the other side, on the high energy side, we have the corresponding anti-bonding level of pi. So, the pi star will be of low energy, since sigma is mostly stabilized. So, if we consider this as the corresponding central part, that is the very center, so we have the sigma star level is of here. So, within the bipyridyl molecule itself, we have some ultraviolet spectrum. So, ultraviolet spectrum for the corresponding bipyridyl molecule can show us that we can have certain transitions, which one is of low energy transition is the n pi star, and the most probable one is the corresponding pi pi star transitions. Now, these bands are already there, and these are basically seen in the visible region. So, UV region, sorry. So, they are seen in the UV region. So, they are of high energy. So, now in at certain points, if the during the formation of these bonds to the bipyridyl molecule, if the corresponding metal orbital is coming over here, so this metal sigma or the metal pi level, the field level, the metal field pi level is coming over here, and if these are then responsible for the donation, that means these levels are also filled, the metal orbitals are also filled, and if they can donate the electron density to the pi star level of this molecule, we will find that this can show us the corresponding metal to ligand charge transfer transition. So, that is the typical mechanism where we see that how and why the ruthenium tris bipyridyl compound is showing the corresponding transition. So, we have mostly a very broad absorption band. So, several closely spaced other levels are also available, is due to the excitation of electron to the various vibrationally excited states of the pi star electronic state. Why this particular signal is broad? Because this we can see that whenever we have a particular electronic transition, and which is basically structured and broad. So, the transition is broad and structured. Why this is so? Because whatever transition we are talking about based on the metal level as well as the pi star level of the ligand, so it is L pi star and say this is M pi say. So, L pi star and M pi is involving for the corresponding electronic transition, and we find it as its corresponding separation is the corresponding delta E value for the corresponding amount of separation between these two levels. Now, we have within this electronic state, since we are talking that we have the corresponding D levels for this MLCT charge transfer transition, what we find that this particular transition we can consider as the metal D level to the ligand P level, because the p orbitals are involved for the formation of the pi as well as the pi star level. So, this is the situation where it is mostly allowed. So, highly allowed transition can take place from D to P, and due to this, and another also good thing is there, since the ruthenium is present in an octahedral geometry. So, we have 3 bipyridine groups are there. So, these are the 3 bipyridine ligands attached to the ruthenium center, and which is centrosymmetric, that means I is there, and which is fully controlled by the corresponding symmetry group, which is the octahedral symmetry group. But the change in this particular ruthenium nitrogen bond, because the thermal vibration is always taking place such that we can destroy the corresponding I for the molecule due to vibronic coupling. So, the molecular vibration is taking place along the ruthenium nitrogen bond axis, and we just basically, because some of these bonds are getting stressed and some are squeezed. So, the I is lost, is not typically centrosymmetric, and due to that loss in the centrosymmetry, there is the corresponding symmetry requirement for this is relaxed, and we have certain amount of allowed transitions due to that. So, that vibronic coupling is also basically giving us some of the other vibrational levels for this molecule. So, within one particular electronic state, so we basically get the corresponding levels not only for the metal center, but also for several other vibrational levels where V is equal to 0, 1, 2, etc. Similarly, for the excited state, V is equal to 1, 2 and 3. So, we can have along this particular transition for these electronic transitions, we can have several other transitions from V0 to the other levels. So, these transitions can also take place along with this transition, which is mainly required for these delta A values. So, that is why if it is centered for this, that means if it is centered for this delta E value, we can have certain smaller and certain higher transitions due to the different transitions what we can have for the different vibrationally excited levels which are available for the excited state, which is L pi star level. So, due to the possibility of several other vibrational levels which are closely associated with the L pi star level, we have a very broad signal for this particular compound for its corresponding MLCT transitions at the pi star electronic state. So, we have the light energy which is falling on the system, and light induced reactions can originate from outer sphere charge transfer excited states. So, we can have, because for the compound what we can have, one particular complex species is there, and on the outside of the coordination sphere we have another species if we can have. So, in certain cases we have these outer sphere charge transfer excited states at the same time, and they can play some important role in the field of photochemistry of coordination compounds. So, this particular thing is also related to certain amount to the photochemistry, because we are giving certain amount of radiation to excite the system from the ground state to the excited state. So, if the supplied H nu is such that means the photons are falling on the metal complex, and we expect that certain chemical reaction can take place followed by the corresponding absorption of the photon energy. So, if we have the corresponding facile transitions for this MLCT type, so at this particular wavelength we get basically the corresponding molecule. If we pass this radiation continuously to the molecule, and the entire molecular system can absorb all the radiation which is falling on the molecule, and so all the molecules are getting excited to its first excited state. That means the excited states due to the corresponding charge transfer transition due to metal ligand charge transfer. So, this particular radiation can excite the molecule from lower level to the higher level, and if we have certain species of two part, that means the cationic part and the anionic part. So, this is the cationic part and this is the anionic one, and we can have different species. That means, if here we have M1 species and here we can have M2 species with certain ligands, that means L1 type of ligand, and here also we can have L2 type of ligand. So, if we can see that one particular system is behaving as a corresponding charge transfer species, the other can be of opposite type, then we can see that a complex type of charge transfer transition can take place when we have the corresponding outer sphere excited states. So, in these cases basically, if we can have a compound like this is of this particular complex where we have a part which is a cationic part and we have the corresponding anionic part, and they play some important role in the photochemical transformation also. So, if we have this typical compound, we are calling this as ion pair, but is a typical corresponding compound recording upon the corresponding amount of this particular species. So, this can be the whole thing can for the charge balance which is 3 plus and this is 4 minus, that means the metal is present in the bivalent state, but this is in the trivalent state. So, this particular for charge balance, so you can have like that our Prussian blue type of structures where iron is attaching to that particular ferrocyanide and ferricyanide system. Here we have this can be the whole 4 and this can be whole 3 to get the corresponding charge neutral species for these. So, when we dissolve these in water solution, we see they basically display first thing that this when M is present as iron, ruthenium and osmium, they all display metal to bipyridyl. In this particular case is the rhodium one, outer sphere MLCT absorptions at 480 nanometer for when iron metal is iron, 400 nanometer when it is osmium, and 379 nanometer when it is ruthenium. For a series of iron, ruthenium and osmium where this basically are changing. So, this particular one in this case what we have seen just now for the corresponding ruthenium compound for the bipyridine also. So when they are bound to this particular case, they can show the different types of charge transfer transitions in certain complex species also. So these outer sphere charge transfer bands can shift to lower energies in order of increasing reducing strength. So if this MCN whole 6 4 minus is present and they have different half wave potential, if we measure it by cyclic voltammetry, we will find the corresponding half wave potential values. The E half values are varying from 0.19 to 0.70 for iron to osmium to ruthenium. That means the corresponding reduction potentials, the more and more we is basically going for positive value as we move from iron to ruthenium. So this basically gives us a corresponding clue for the corresponding shift in lower energies as we move for complete electron transfer, because the reduction is nothing but the complete electronic charge transfer from one orbital to the other for the species like iron for its reduction, osmium and its reduced form, and the ruthenium and its reduced form. So when these are present for iron, osmium and ruthenium, they are all in +2 oxidation state. So when you go for their reduction, they will be forming in the +1 oxidation state. So next we will just see that other two types of categories for these charge transfer transitions, where we see that ligand to ligand charge transfer transitions are also important. So earlier we have seen that metal to ligand charge transfer and ligand to metal charge transfer, that means we are basically talking certain systems where we have the metal ligand bonding, and either the metal is transferring the charge to the ligand orbitals or ligand is charging some metal orbital. But now we have reached and we are going to discuss one particular situation where both the two parts are the ligands. That means they are present in the system where it is bound to the metal ion, and where we have this ligand also, and if we have L1 is one type of ligand and L2 is another type of ligand, and they are still bound to the metal center, but one type of ligand is highly oxidizing and other type of ligand is highly reducing. So if this is reducing and this is oxidizing, so the reducing ligand center can transfer the electronic charge to the oxidizing ligand center. So for transfer of charge, so they are bound to the metal ion, but the corresponding charge transfer is taking place basically between two ligand systems. What we have seen earlier, for a particular single ligand system, we can have the pi level as well as the pi star level or the n level. So in that particular case, what we see, the pi star level is donating the electron density to pi star level, and the n level is donating the electron density to pi star level. Now the situation is, if this is for L1 and the other one is for L2, so this particular pi star, it may not be of same energy, and it has also another pi and it has also another n. So the L1 molecular orbital level, the ground state level, is the donor level, and acceptor level will be on L2. So we have the corresponding transfer of charge density from L1 to L2, and which is basically going through the metal. So metal is basically functioning as a bridge for this type of charge transfer. So we have the LLCT type of charge transfer in this particular case. So here we get basically intense absorption bands which can be assigned to inter-system ligand to ligand charge transfer. That means the system has two different types of ligands if possible, and transitions appear in the electronic spectra of square planar complexes. So this particular area is very rich. Some of the groups around the world, they are working on the square planar compounds of nickel, palladium and platinum species, which contain a 1,2 ethylene dithiolate type. That means the sulfur bearing ligand, where the sulfur donor groups can donate their electron density very easily, because sulfur donor atoms are very big in size and they cannot hold this particular charge to them. They donate the electron density very easily to the other system. That is why all sulfur bearing compounds are prone to oxidation. That means they can donate the electron density to some other acceptor level. So if we have any sulfur bearing compound, what we have earlier seen, that it can be dithiocarbamate or it can be typically quinaxolone dithiol, which can be prepared very nicely SH, or it can be the xanthate type of ligand. So whenever we have this sulfur, so we have this higher electronic charge on these sulfur groups. So this can be donated, or we see the corresponding oxidation. So this is the typical type of ligand system which can function as electron donating ligand. For the corresponding ligand to ligand charge transfer transition. So other type of ligand, what we can have, the typical diimine type or diamine type of ligand, which can be simple ethylene diamine or which can be simple bipyridyl type of ligand, where we have seen that bipyridyl type of ligand can be a very good acceptor ligand for metal to ligand charge transfers, what we have seen. So this is one simple drawing. Basically for that we can have so many types of sulfur bearing ligand. If it is for ethylene dithiolate, so ethylene backbone will be there, which is typically a rigid one, which is present also over that QDT2 minus, because two of them can go for deprotonation, giving two charges on these two sulfur. So it is quinaxolone dithiol type of group. So we have a rigid backbone. So this backbone is typically rigid. So the rigid backbone is also required for their corresponding donation, and we can have at certain point that if we have the typical oxidation, then we can get the corresponding sulfur sulfide coupling. So is for full oxidation of the ligand system on the thiol type of ligand system, basically we will end up with sulfur bridge species. So which is full oxidation and full transfer of electronic charge, 2 electron oxidation for this sulfur bridge. So we have the sulfur backbone, and then we can certain diimine type of ligand. So diimine is very easy to visualize or easy to consider. So one such diimine type of ligand, so we can have the glyoxal, then simple NH can be there. So glyoxal plus ammonia give rise to some diimine type of ligand system. So where the carbon nitrogen double bond is there, and that carbon nitrogen double bond can have what we have discussed just now, that we can have certain orbitals which can be the corresponding acceptor orbitals. So they have the pi star orbitals on these groups, so they can be very good acceptors. So we have the donor level on the sulfur bearing group and the acceptor on this carbon nitrogen groups. So we have from the donor to these acceptors, we have the corresponding LLCT charge transfer. So we have this particular backbone where basically that what type of ligand we are. So it's a typically it is not always very easy to make this compound of nickel, palladium and platinum, because in most of these cases we have the corresponding homoleptic species, that means both the sulfur ligand bearing molecule we can have or both the nitrogen bearing molecule we can have, but to make this heteroleptic compound, that means one dithiol and one diamine type of ligand, is very difficult to make sometimes. So some experimental manipulation is there, so some procedure is always there where we can make these molecules in a typical way. That means first we can make the corresponding dichloro compound the way we make it for the platinum, having two ammonia groups and its chloro derivative. So this is basically the well known molecule what we talk about. The corresponding drug also for anti-cancer drug is the cisplatin. So this molecule, if we go for that and if we can able to get, because when they go inside the cell, these platinum chlorine bonds are getting hydrolyzed and they are basically going the corresponding replacement for water molecules. So in this particular case, so certain basic background we can have for this type of synthesis is that if we use simple silver nitrate to take out these halides from the platinum center, we have the corresponding diaco compound, and then any of these ligands basically we can use this S and its corresponding sodium salt, rather S minus Na plus H minus Na plus, then we will end up with a compound like this where we have nitrogen and sulfur environment around the platinum center. So we have the mixed or the heteroleptic species based on the platinum compound, which is square planar. So this geometry is also important, that it should be square planar for this site of electronic transition. So energy of this transition is almost independent of the metal ion in the bivalent oxidation state. So whether we are making a nickel compound or a palladium compound or a platinum compound, the corresponding transition energy or the lambda max what we get for this LLCT transition is of closed energy. That means the metal orbitals are not involved in this ligand to ligand charge transfer transitions. So which is a very important clue that how we can identify that a particular charge transfer transition is not of MLCT type or LMCT type, but it would be of LLCT type. So if it is metal independent nature, that means if we have three different types of complexes of the same metal ions, metal sites, then we measure the corresponding lambda max values, and those values can immediately tell us that if they are of same energy or close to same energy, we can tell them they are originating for the corresponding ligand to ligand charge transfer transitions. So we have the last category is the MMCT type, where we have the cationic cobalt amine complexes which we can find for the two forms, that means the hexacyano iron 4 minus, that means the corresponding ferrocyanide species and the corresponding ruthenium analog, and if they form basically in pairs which are characterized by corresponding outer sphere MMCT transitions. So cationic cobalt compound is present and anionic this particular part is there, then only the metal orbitals are responsible for the corresponding transitions. So short wavelength of these absorptions is due to the large reorganization energy which is associated with the reduction of the low spin cobalt 3 compound. That means the cobalt 3 compound is there and the cobalt orbitals are really available for the corresponding acceptance of the charge density, and since an electron is accepted into the antibonding Eg orbital, the MMCT transitions require large extension of the cobalt ligand bond distance. So, these cobalt amine compounds are therefore basically responsible for accepting the electron density, and the corresponding metal orbitals on these hexacyano derivatives are there, which are basically donating the electron density. So, that gives rise to the last type of, or the fourth type of corresponding charge transfer transitions, where two metal orbitals are involved and we get the corresponding metal to metal charge transfer transitions. Thank you very much.